Now, let's look at the system and then you understand better. The idea is the same. So we are using here also the red beam, and here we are using an amplifier. We are using it as a gating pass. And the good situation here compared to the upconversion, that in the case of upconversion, we have, as I said, that we have to fulfill somehow the so-called phase matching in the case of the nonlinear crystals. So we have to change, actually, depending on the fluorescence wavelength, we have to change the angle of the crystal if we want to pick up another wavelength, what we want to look at. In the case of Kerr gates, this is not needed. We are looking for the whole spectrum, actually. You will see how. This is very easy, actually. It's an easy method. It's a very good method. So we have our laser here. So it comes via the stage. And first of all, if we go in this direction, we have our BBO, and the BBO nonlinear crystal. We do the second Hammond generation, and we have a blue light. And with this blue light, we are exciting our sample, and we will have some fluorescence. We collect this fluorescence with the help of two Cassegrain objectives, so Cassegrain mirrors, and actually they are here. So this is the sample holder, and these are these two Cassegrain objectives. So they, after that, in the second one, it will focus down the fluorescent light. Now what happens that we put a polarizer here, the first one, between the two Cassegrain objectives, and we will put another polarizer later, actually at this point, which is the third Cassegrain objective. And these polarizers are cross-polarized. This means that in a normal case, no light goes through these two polarizers because they are cross-polarized. Now, the fluorescence light will go through only in that case if we rotate somehow if we do some anisotropy in this so-called Kerr material. But if we focus down basically on this material, the red light, actually, this will introduce this small anisotropy in the optics. If you change the polarity slightly, it will rotate, and this means that a small portion of the light will go through the second polarizer due to this induced polarization here. And actually, the Kerr material can be many things. The easiest Kerr material is CS2, and this is the most loved Kerr material. The only problem with that one, the Kerr effect is very, very high. The disadvantage that the relaxation is slightly slower, so it relaxes back in 1 picosecond. And of course, if you want to measure something sub-picosecond, that's a problem. So instead of this, we were using some fused silica plate when the Kerr effect is much smaller, but the relaxation is much faster. You can use something in between. So you can use benzene, and if you use benzene, your relaxation is roughly 500 femtoseconds. So this is how it works. And basically, at the end, as I said, the changing or moving the stage, you will select the timing when you couple out the fluorescence light. So basically, you can couple out at early times or later, and you are collecting basically whole spectra at different time steps. So let's look at the results. Now, this was just a comparison, as I mentioned, of the Kerr materials. We have the Suprazil, and this is the shortest one, and we have the benzene and the CS2. And this is just a close picture of the Cassegrain objective, and this was the pickup mirror. Here we have this pickup mirror, which picks up the red light, actually, which is coming from this way, and this is the pickup mirror. Now, okay, so we measured the fluorescence of of the so-called MTHF in the photoliths. Well, this is a photoliths mutant, and I haven't mentioned that in the photoliths we have an antenna which can absorb the blue light. And actually the nice thing is that most probably have learned about fluorescence lifetime, fluorescence energy transfer already. And this is a method what we are using in order to investigate protein dynamics or things in the cell. The funny thing is that this happens in the biology. So the antenna absorbs the light and transfers its energy to the FAD inside the protein. Anyway, in this case, we are measuring the fluorescence lifetime of this antenna, and this is on a shorter time scale. And now, let me show you the whole measurement. Yeah. So this is what we do here. So we are measuring at different time steps, basically. We are measuring the spectra. And if you look at the spectra, you can see two different things. This shoulder, actually, it comes from the antenna, and basically this part of the spectrum comes from the flavin. So because you can see two different things. And now if you measured basically the lifetime of the antenna, when we have the FAD also in the protein, you can calculate the distance between the antenna and the FAD due to the FRET concept actually. How does it work? Well, in a solution, the MTHF, the fluorescence lifetime of the MTHF is 354 picosecond. Now, if you measure it in the protein, it's only 23 picoseconds. So basically, your energy transfer, the efficiency of your energy transfer is 0.93. Basically, if you stick in the numbers, you will get that the distance between MTHF and the flavin is 17.5 angstroms, which is actually very good or very cool indeed, because this reflects back the structure, the X-ray structure of the photoliths. So basically, using Cargate method, you can give these type of details. So this is Cargate in action. So this is a very good thing, I would say. And now, this is what we measure. We also measured the fluorescence lifetime of the FAD in the photoliths. In the case when MTHF was not there, it's a small detail. But if you make a mutation, small mutation in the protein, in the sequence, so the protein will be expressed in that way. We don't have the antenna. The antenna is bothering us because it absorbs the light at 400. It's very close as it absorbs the flavin. So that's why we don't want it. So this is only the fluorescence of the flavin. Now what you can see here is simply the Raman scattering of the solvent we are using here, which is very, very nice actually. You can see even that one. So now, if we measure basically at, let's say, at 520 the fluorescence lifetime, we have a very fast decay, close to 6 picosecond, and as I mentioned, in the free form of the flavin, that was 9 picosecond in water. So it's different. The details are somewhere elsewhere, so I can tell you the details if you are interested. But this is how the technique works actually. So now let's jump to another different technique, fluorescence technique, which is basically the most loved by me. And this is transient absorption spectroscopy. This is also kind of pump probe method actually, and the idea and the concept is very, very easy. The thing is that we have a pump, excitation pump, and we're exciting our sample, and we are probing at different time steps or different time delays, and we will get a spectrum at different time delays. Now let's see how does it work. So we have this excitation, and we have the probe beam, and on the CCD we will measure spectra, which is good. Now what do? We just move the stage slightly. This means that the difference between, or the delay between the pump and the probe will be changed. We just excite again, we will probe again, and we will have another spectrum. So this is what we do. We are measuring the change in the absorption or induced or absorbance change at different delay steps or different time steps, and we are gathering all the spectra. Now, this is our system at work at the University of Page, and this is of course our delay stage. This is the amplifier where the beam comes from. So you can see this is red, and it will be red until the first BBO. So after the first BBO it will be a blue beam already, and the white beam actually, this is the so-called white light continuum. I will talk about in a minute. And this will be our probe actually. And what happens here, that after the BBO we will have a blue beam, and it goes to this corner cube, and this will be our excitation beam for the sample. We will excite the sample with this blue beam, and we will pump it, or we will probe it with this white light continuum. Now, what is a white light continuum? White light continuum, it's, I won't go into details because we don't have time for it, but anyway, if you have a short pulse like this, if you put anything, a piece of glass or glass of water or something, that will produce you white light. And this is, it will be something like this. Depends on the material that how wide will be your continuum. And of course in our situation we need something, the wider is the probe, the better it is, because the bigger spectra we can cover actually. And what we have here, maybe it's not so easy to see it, the region we have is here from 400 to 650-ish or almost 700. We can make it actually bigger, we're playing around a little bit. Now what happens here, that this is, this optical material we have here is calcium fluoride, and calcium fluoride gives you quite a wide white light actually, between 400 700, and 400 is important for us, from 406 to 500, because we have many interesting things happening there in the flavor proteins. That's why we are using calcium fluoride. The only disadvantage of calcium fluoride is you have to move it faster or slower, doesn't matter, but you have to move it, otherwise it will crack, as the pulses are quite energetic here. In the case of if you have a sapphire window, you can use, or you can use other windows as well, which have better thermal properties. You don't have to move them, but you restrict your continuum to 500 to 700 region. So that's the idea, to use the calcium fluoride. And actually we are using, in the case of the NOPA, non-covalent optical amplification, we are using sapphire windows that's not there. But here we need this one. Now this is just a small example what happens. So if we have this white light continuum, if you put a sample, this is an octaedral porphyry, if you put your sample in the beam, you will see the absorption actually. You will see the absorption from the sample, and you will see the change in the absorption or induced absorption in your measurement. Now, this is just a small picture of our system in Page, and this is the panel what we are using for the measurement. And basically, if you put your flavin or FAD in water, this is what you see. You see the so-called bleach, you see excited state absorption, and you see the so-called just a moment. And we can set the numbers here, the exposure time, the number of kinetics, and averaging depends on the sample, how long you have to average basically. And So typically one measurement goes to, well, 25 minutes. This is the shortest measurements, and we can have longer measurements. Let me show you just an example of these measurements. What is the primary data we can get after measurement like this? And let's step out from here. So what you will get is kind of heat map here, and these are, if you take a slice from here, you will see the spectrum, and if you take a look in this way, you will have the kinetics. So this is the primary data we have, and let me show you. So you can see that different time delays, we have different spectra. Now, if you take a look, this is before zero. So before zero, when the probe was before zero, before excitation, of course we have nothing. This is just noise on this side. If we move, and now what you can see is the so-called coherent artifact. This is how you know exactly when your zero is, because these huge noise appears, and now it clears up, and now this is your spectrum basically, and this you will see that as you are increasing the time step, so the time delay between the pump and the probe, this will fade away, exactly how the excited state will fade away after excitation. And of course, you can check the kinetics at different wavelengths, and if let's say this is at 500, this is the kinetics what you have, and you can take a look at early times if you're interested in the early kinetics. Basically, this is what happens here. And also, basically, this is a three-dimensional data or 3D matrix. So you can open it this way, and we can plot this 3D matrix. This is what you have. This is the time step with this direction. This direction is the wavelength scale exactly. So this is what you see, that this is the bleach relaxes back in picoseconds basically. So this is what your general data or your primary data you will get from transient absorption. Now, as I talked to you a lot about the flavins, and of course we tried out the system for FAD, which has a short fluorescence lifetime. And of course, we can see that the oxidized flavin relaxes back quite fast indeed. And we have a 10 picosecond relaxation here at 500-ish wavelengths actually. This is what we measured just recently. This is basically a test measurement. Of course, we use this method for many things, and among them, we use this method for APA. As I mentioned, in APA, the primary steps are very fast, and indeed, and this is just a measurement. You don't have to understand this, or you don't have to memorize this, of course. This is the dark state of the protein, and this is the light state of the protein, which is very interesting actually, that the relaxation in the case of the light state, which is this one, it's much faster than in the dark state. And what happens in the case of APA, nothing else, there is no electron transfer there, as we proved. What happens is a reorganization of the hydrogen bonds around the flavin. But I will talk about this slightly later. So indeed, it's very interesting how it affects already electronic states or structure. Now, of course, it's kind of a subcase, can be a subcase of transient absorption, but it's kind of different from the visible absorption, of course, the infrared absorption. And this is much more difficult to do. So this is, I would say that you cannot do it in your lab, only in the case if you have a lot of money, transient infrared absorption. So in one of our colleagues, he did it in London in his lab. He got a lot of money for this, but not many labs have that amount of money. So it happens at research complexes, and the research complex I'm visiting is called Rutherford Appleton Laboratory, and this is the C-Lab, the central facility that we have this apparatus we are using for transient infrared absorption. Actually, the central laser facility has a couple of different laser projects. They are all interesting. They have, in the Astra and the Vulcan, they have very high intensity lasers, and also at a second pulse generation as here in Eli. And we are using smaller energies and nicer lasers, or milder lasers in our case, the laser for science facility, for vibrational spectroscopy and for laser tweezers, and also from microscopy system which is called Octopus, if you have heard about. Now, this is the LSF user community, and this was a meeting a couple of years ago. So these are the guys who are using these lasers as a laser facility. And this is a new building we have recently. Actually, just I put this picture because what happens that this is a building. So here we are producing the proteins for the measurements. This is the guy who is the main protein purificator guy. And later downstairs we have the laser systems. These guys are working hard on the laser system to have the nice and the proper wavelength of excitation. So we take the protein from upstairs to downstairs and we are measuring them. Now the idea, it's also pump probe, it's very, very easy. So we are pumping with a blue beam, and you can see that the blue beam is the first one. This is the excitation, and basically what we are doing, we are increasing the time between the blue and the red beam. So we are measuring, we are probing at different time delays, and we are measuring either higher absorption spectrum or Raman spectrum, depends on the situation. So now these are details what we don't need to know. This is how it looks like actually. At the end, this is our sample holder. Now this is a problem, of course, gives us many different problems, because in order to avoid high absorption in the infrared, because if you think about your protein, you have the polypeptide chain, and of course you have amide 1, 2, 3 absorptions. So if you have your very dense or protein, or your cell is very thick, this means that you'll absorb all of infrared light. So you have to use here thin cells. So typically we are using, this is a Herrick cell, and we are using the calcium fluoride windows with a spacer, and we have a 50 micron spacer. That's our most general measurement, basically. The problem is that if you want to have some signal from this amount of sample, you have to increase the protein concentration, and typically it's about 1.5 to 2 millimolar protein concentration here, which is quite high, I would say, quite a lot. So this is a disadvantage compared to, let's say, fluorescence or visible transient absorption. Now what happens here, that we are exciting with the blue beam, and let's say we are probing with this purple beam or the other, which represents the infrared beam here. Now the idea is very simple. So this is our pump, and it goes through the sample, and this is our IR probe, and this is go through the sample as well. And what we are measuring basically the transmission on the detectors. And actually the detectors are also crucial in this configuration, because they are very, very, very expensive. So this is the primary data what we are measuring. And as I mentioned, if your protein itself has a huge absorption, normal steady-state absorption, this means that you will have very small absorption, very small amount of light going through your sample. That's why you have to decrease the thickness of your cell. And basically what happens here, that you are, in the case, before pump excitation, you have a normal absorption in IR. After the pump excitation, basically, you can have absorption, an induced absorption, basically which will be positive. If you subtract them, the second one from the former one, the previous one, you will have the difference absorption spectrum. This is how it looks like. You will have the bleach states, or these are the ground state modes, and you will have the so-called transients, which are the signs for the induced absorption. So this is what you have. And of course, with the pump, you are exciting your molecule in the excited state. So if you measure, basically, the kinetics here of the bleach or the transient, you will also measure the time or the relaxation time as the excited state relaxes back. So now let's look at the primary outcome of this measurement. It's very simple. This is at 2 picoseconds after excitation. This is 100 picoseconds after excitation, and this is 500,000. So you can see it after excitation. This will decay back to 2,000 picoseconds, and basically these are all the spectrally measured all together. Now, of course, we have to know what are these modes stand for. Otherwise, our data is worthless, basically. Say it loud. Okay, so of course, what has to measure as FAD, because this is the easiest. We can excite with 400, and we can have a very good high concentration from FAD. So this is our test measurement here. In FAD, we have a couple of interesting peaks. This is the strongest one, it's the bleach at 1500, and basically this will be the vibration of the isoelixazine ring. And this is what we measured here, and we have a nice relaxation actually. And if you compare the number from here and the number we measured with fluorescence or visible absorption, we will get the same numbers. Now, of course, we have to identify somehow the modes, and this is also a very, very long story, and I won't go into details, but basically, in the flavor proteins, we have a strong mode here, strong bleach around 1700s, and based on our research and our studies, this strong bleach here stands for the C4 carbonyl, basically. The stretch what we have is C4 carbonyl, and this one, which we have at 1650-ish, that stands for this C2 carbonyl stretch. And basically, this one is from the big bleach comes from the vibration of the whole ring, basically. This is what we know. And actually, this was a special mutant, and that's a very different story when we saw this very big bleach actually in this mutant, and we spent quite a lot of money and a lot of time to identify this peak. Because initially we thought that what happens in the flavors in other cases as well, if you have less and less hydrogen bonded flavin, it will be less and less hydrogen bonded here, and the C4 carbonyl, that shifts up the frequency. And we had to check whether in this mutant we are talking about this upshift or the reason is different. Actually, it was different, but for that one we labeled, or we used C13 carbon in our sample, so we expressed the protein to contain C13 carbon instead of C12. In that case, all the protein modes were downshifted, and in that case, turned out that this peak doesn't come from the flavin. This is its origin is somewhere else. Now we have something I don't have time to explain in details, but basically what happens here that this is also a pump probe method, and we are exciting with a blue beam or with some kind of beam at the very beginning, and with electronic devices, we can use 10 other probes, actually at 10 different time steps actually, and we can have a probe at every 100 microseconds. In this case, we are extending our time resolution from the, I don't know, couple of hundreds of femtoseconds up to 1 millisecond basically. Because at every time what happens, we are changing the optical delay stage, that's okay, and we have these short delays as before. But we are adding additional 9 or 10 probes at every 100 microseconds. So if your, let's say, time delay is set to 1 picosecond, this means that you will measure your sample at 1 picosecond, 1 plus 100 microseconds, 1 plus 200 microseconds, and so on. And this is how you reach up to 1 millisecond, and we can get actually quite a lot of good information based on this. This is how it looks like. For this one, you need two laser systems, and we are using the same clock actually, the same oscillator, but we are using two amplifiers. And we have this is our pump laser, so it pumps at every millisecond. But between this one, we are dividing this pump down to equidistant 100 microsecond probes, infrared probes. This is how it works. Now let's jump. We had plenty of results on this, but we don't have time to explain it. But the idea is that we saw actually very nice decays and very nice protein dynamics on the microsecond scale, which proves for us and that in APA, the original excitation, original hydrogen reorganization which happens on the picosecond scale basically triggers a larger conformational change, a larger change in the protein on a time scale of a couple of microseconds. And this is just a detail. This was a JAX paper where they highlighted our results, and we were of course very happy. And these are my colleagues, whom I own acknowledgements, of course, to Professor Stephen Leach at UEA, Professor Peter Tong at UEA, over to my colleagues and to the guys at the University of Page. So thank you for your attention, and maybe we might have some couple of minutes on questions if you have. Okay, any kind of question? Just a small question, please.
One very small. I'm not so familiar with the field. So in terms of transient spectroscopy, what is fast in terms of tuning? What is fast?
What is
What
fast?
level that is fast? Because in OCT now there are two lasers, so very fast, megahertz. So in transient spectroscopy, what is the technology nowadays?
We don't.
Kilohertz, 10 kilohertz?
Actually, we don't need megahertz usually. Actually, this is too fast for us, because in this case, in let's say in the photocycle, in some cases, in the flavoprotein, it happens in less than a millisecond. It's good. This means a kilohertz laser. So if your laser is faster than that, you will re-excite again before the photocycle was done. Of course, we can avoid this. But basically what happens in the normal cases, or in the most general case, we are using lasers between 1 kilohertz up to 10 kilohertz. That's the most normal. Or this is the typical. And actually on the field they are provided, or they are selling these lasers, that you have the option between 5 and 10 kilohertz. The only disadvantage, or the only problem, if you are using a 10 kilohertz, let's say a Spitfire laser, it's quite hard to realign it, or it takes some time to realign if you want to use it at 5 kilohertz. But that's a detail. But anyway, we don't need more than that. The oscillator itself at the beginning, but of course it's divided down. In the beginning, the oscillator is 100 100 megahertz. It works at that repetition rate. And what we do actually, even in our lab, I'm not using at the moment, we have a 2-photon microscope, and almost 50% of the beam goes in that 2-photon microscope, so we can use it for 2 photons. And but the rest goes in the amplifier, and that goes with 1 to 5 kilohertz. Basically, this is what our system works at.
And recognition of spectrum, how is that done? Do you match patterns, or do you look via, let's say, an FFT?
Basically, it depends on the situation. The visible and also in the infrared, you match patterns. Basically, yes, we have some test samples, or we have some very known molecules, and we are comparing them. Especially infrared. Infrared is more complicated, I would say. So that's why we start always with a known sample, with known vibrations, and but we are not really using FFT, or not at all, basically. Yes?
As you told, in the basis of this technology, photomixing we use as nonlinear process. Is it different, use second harmonic generation or third harmonic generation? I want to know if either of these techniques may be affect, or they are equal to be used, to be applied.
The only problem with third harmonic generation, we have a couple of problems with third harmonic generation, and it's not so easy to do. That's the main problem. Otherwise, my colleagues, with microscopy colleagues at Ecole Polytechnic, they were using it, so it's not so bad. So if you have the right crystals, you can do that. The problem is what you want to do that with the third harmonic generation, because you have your laser, let's say at 800. This means that you have a 400 photon from the second harmonic generation. Now you are using your 800 again. You put your 400 photon, you are mixing in the second VBO, and you will get something 265, I guess, nanometer. Now with that one, you can excite the tryptophans, which can be exciting, or it's good, but not very good for imaging, I would say. And for that one, if you want to do that, you need special optics. So you have to really in the UV region if you want to excite with that one. But otherwise, you can use it. And actually, of course, we have a plan to use it in the near future, actually. So my colleagues back at UEA, with that system I just showed you, they are doing basically third harmonic generation already, because they are exciting the tryptophans, and they want to look at the tryptophan fluorescence. So that's the idea. In my case, I chose so far the easy way, because the easy way is 400. You put your crystal, and even if you had a very bad day, you will have second harmonic generation. So you have to do pretty stupid thing not to have it. You're welcome. Okay, so if you have no question, maybe I can answer it later.